Hi everyone, in this video I'm going to explain more about electron configuration, which is this like 1s1, 1s2. We talked about this in class a little bit, but just to kind of go over that again, and then also to introduce this idea of an orbital diagram, which looks like this. So we've been learning about this new model of the atom, this quantum mechanical model of the atom, and then part of that is understanding how the electrons are configured or arranged inside an atom. So where we've left the situation so far is that we've worked with this kind of diagram previously. It's a dot diagram. You've got the nucleus in the middle, and usually we used to use the symbol of the element and then draw shells, right? Electron shells, dots or X's to represent electrons. So you might be familiar with this one. This is where we're at recently. We've learned that this model doesn't explain lots of the chemical behavior of an element. Excuse me, and it's not sophisticated enough. Also, electrons have negative charge. So this model doesn't explain how all these electrons that exist in atoms, and obviously some atoms are really big and they've got lots of electrons, so how do they all exist in the same small space and not repel each other too much? So we've come up with the idea of subshells or sublevels, and we've got S level, P level, and D level, and also F level as well, and they all hold different numbers of electrons. And then also from the emission spectra, which was the looking through the little black box and seeing the lines for the different elements, the idea of energy levels helps explain that phenomenon as well. So these things have all built on each other up to about here. And then in the notes, we've maybe you've got this far, but if you haven't, it's okay. We're going to touch on this idea of orbitals next. So this is where we've been, this is where we are, and this is where we're going to get to today. So the model of the atom is not this sphere, right, and the electrons go round in neat circles. They don't exist like that. So that's led to the idea of energy levels, and then also within each level you've got sublevels, and then they have different shapes. They've got different shapes depending on how many electrons are in them and how close they are to the nucleus. S sublevel is a sphere, and it holds up to 2 electrons. It starts nice and simple, then it starts to get more complicated very quickly. The P sublevel holds up to 6, and so this is kind of the all-together version. But if you imagine that there's an up and down, a left and right, and then a forwards and backwards, so 1, 2, 3, and each one holds 2. So the idea of this sublevel is the electrons are going moving between each one. So if this had 6 electrons inside this area, 2 would be going up this way, 2 would be going this way, and then 2 would be going this way. Also, if this, for example, if this was the element that we were looking at, it would have all of these levels before it got to this one. So we can't just have a 2p level without a 1s and a 2s. So it would have a 1s sphere. Kind of imagine it right in the middle of this where the nucleus would be. Kind of around that, so kind of overlapping it, would be a 2s, and then you'd have this thing on top. So the 1s and the 2s would be inside here, and then deeper inside would be the nucleus. So it starts to get a little complex and a little difficult to show you accurately. And then imagine if we add another 3s, another 3p, and then a D, a 3D, right? It starts to get a little crazy, but that's, you know, kind of the explanation that we have for electrons, which have negative charges, and they move with lots of energy, and they exhibit this unique behavior. So we've got to kind of explain that here as well. So electrons, kind of early in the quantum revolution, electrons were found to have wave-like properties, and then if they have wave-like properties, if they behave like waves, then calculations that existed at the time for different types of waves, like visible light and so on, different wavelengths of light, those calculations could get used on electrons. And then when that happened, that's how Schrödinger, who's one of the people that contributed to all this quantum revolution, one of the many people. This is how he arrived at this idea. So orbitals is kind of the new name for these sublevels. So s orbital, p orbital, d orbital. It means the same thing, but this is just this was before the idea of orbitals. And the orbital is just an area around the atom where the electrons could be. There's about a 90% chance that it could be there. So what we're saying is that this is still true, right? But we're going to shift the name to orbitals. So each orbital holds a certain number of electrons. So the S, for example, the sphere, would hold up to 2. And there'd be 2 electrons moving around in here. There's a bit more to say about it, because they don't just move around in here, they've got other properties too. But this is kind of the sub-level idea. We're changing it now to an orbital idea. And it's just kind of the shape, physical shape, that exists around an atom that the electrons could be in. And when you did the quantum leap lab with the marble and the target, that was what it was supposed to kind of represent. It's difficult because it didn't show you like orbital shapes or anything like that, but it just kind of showed you that that's the probability of where an electron could be. So that's the goal of that lab. Okay, so if we look at hydrogen here, it's got 1 electron. So if we rotate the electron configuration, and when a good synonym for that is arrangement, if that helps, it would be 1s2. So that's the energy level, that's the orbital or sublevel, and that's how many electrons are inside it. So we've got a new system which we'll expand on this when we start learning more about different atoms and then looking at how they're arranged on the periodic table and explaining some of that behavior. This will become a useful tool. So just to introduce the idea and show you how to use it, it's hopefully not as crazy as it looks, but it's called an orbital diagram. So for orbital diagrams, we're representing how the electrons are arranged. It's basically the same as this, it's just a different way to represent it. So there are some rules that we'll get to that you've got to follow with making these diagrams. I'm just going to erase this, kind of clear up my board a little bit. Okay, so we use the boxes, right? The boxes are orbitals. The rules are that you can't have more than 2 electrons per orbital, and that's the Pauli exclusion principle. So yet another person involved in all of this work. So the idea is that you'll have 2 electrons per orbital maximum. You can have 1, but you can't have more than 1. So for the 2p sublevel, we kind of broke it into 3 boxes. In each box represents kind of the figure 8 shape, right? So the 3 kind of superimposed balloons like this, or pairs of balloons. So that's what this represents this. So you need a little imagination with this unit. Kind of close your eyes and squeeze really tight, and you can just maybe picture an orbital. So that's the rule of Pauli, right? So you've got to have no more than 2. There's a reason why I've drawn these little shapes. It's not, maybe it looks like half an arrow or a number 1. So electrons are a charged particle, right? They've got a negative charge. Charged particles can rotate. So just like planet Earth, they can rotate, and they can also move around. So just like planet Earth, it can rotate, so day and night, and then it goes around the sun in a year. So electrons kind of have a similar kind of property. So they can rotate, and they can move around the orbital, so the shapes that I showed you, and that gives them some magnetic properties. So just like Earth can be magnetic, it's got a north pole, right, and that's due to the liquid core inside moving around, and it kind of generates electrical charge, which generates magnetic properties. So electric properties and magnetic properties are related to each other. So electromagnetic spectrum. So if something's got a charge and it moves around, it causes a change in the electric field and the magnetic field around it. So you've heard about magnetic fields, kind of an area where a magnet would experience a force, like a magnetic force. Same with electricity and electric charges. So electric field kind of like a magnetic field, and each charged particle, like an electron or a proton, has those properties. So we represent the two electrons differently, and so this is, you can think of it as half an arrow, right? So half an arrow shows the spin of the electron. So one electron would spin one way, and then the other one would spin the other way. There's a huge complicated equation, which I'll show you, but you don't need to know until you get to like bachelor's level chemistry. You don't need to worry about it, but just know that we represent the different properties, the different spin of the electrons with an up half arrow and a down half arrow. So this is one electron. Label that here. So for example, this is the orbital diagram of hydrogen. It's nice and easy, there's only one. But if we were going to look at this element, which is 2, 4, 6, 7, so that's nitrogen, sorry. So if we looked at nitrogen over here, we'd fill up the energy levels, right? We follow the rules that we've looked at before, and when we wrote out these, so that still applies. So 1s can hold 2, 2s can hold 2, and then the 2p follows this rule, the 2 electrons per orbital. It can be up to 2, but it also follows Hund's rule, and it's kind of like the empty bus seat rule, right? So you can't have an empty bus seat when you're filling up the bus with people. You might see it called that as well, but this will happen and not this, because this is less energy for the atom to achieve than this. And also, if you think about it, if all the electrons have negative charge and they've got this spin property, it's seems more likely and obvious that they'd go separate than try and force themselves together when there's an empty space right here. So kind of like the path of least resistance. So this is what happens when you fill them up, not this. But this still holds true, this holds true. This is just a different way to represent the orbitals. Okay, so we're changing, kind of shifting the like the name of it to orbitals. An orbital is just that cloudy shape around an atom where the electrons could be. The up and down arrows kind of represent the spin. So one electron spins one way, the other electron spins the other way, and it's how they can exist in a small space and not repel each other too much. So long story short, we've kind of been here working on electron configurations. We're going to start to represent the atom with orbital diagrams now. There's a lot more to say about this. When we start looking at the periodic table in more detail, we'll see how this becomes useful and also really significant in kind of explaining some major chemical properties. So this is fluorine right here. We just did this example. Let's do my favorite, aluminium. So the way that you draw an orbital diagram is very much like what you do here for electron configuration, and I'm going to do both. So I'm going to do electron configuration first. So aluminium has 13. This E with a little negative sign over it is kind of the short version of electron, if I didn't say that already. So it's got 13 electrons. So I've got to fill up lowest energy up to highest energy. That's the Aufbau principle. So I'm going to go 1s2, and then keep going, 2s2, 2p6, so that gives me 10, and then 3s2, and then, 3p1. So we've also learned about the abbreviated versions, and that's the shortcut versions. If you can recognize that 1s2, 2s2, 2p6 is the same as neon, which is all of this. And I think the visual that's in your notes of the periodic table with the orbitals kind of laid out, I think it for me is really helpful, and I think it's a good thing to practice when you work on these, because you can pick out where an element is and then you see what orbitals you'll need. And also you can see this a bit more clearly as well. but we'll do more examples of those in class. So there's my electron configuration. I can also just erase all of this and put neon in square brackets, and then there's the leftovers. So this is saying 1s2, 2s2, 2p6, and then leftovers. All right, so I can do orbital diagram next. So, oh, I wish I'd left it out now because I would have had it already labeled. So you draw the box to represent the orbitals. This is 1s, 2s, 2p, and it doesn't matter if you don't draw perfect boxes either. All right, so following the same steps, let's just use all the colors today. So there's 1s. 1s holds 2 electrons, one half arrow and the other half. S holds the same. Draw my boxes in. So 2p, the way that we've kind of described it here, it's going to fill up this way, but it's not going to matter because you're filling them up anyway, right? So there's the 6, so that's 2e. S can hold 2 as well. So there's 1, 2. It doesn't matter if you draw them down and up or up and down, it's all going to be the same. And then 3p will just have, and we draw the empty ones too, I didn't say that earlier, sorry. So 3p just has 1, so there's, let's draw it the other way, so you don't think I'm lying. And so there's my orbital diagram. So electron configuration, abbreviated, orbital diagrams, kind of follows on from the same thing. Kind of following the same, these same rules. Orbital, levels, sublevels, they're the same thing. They hold certain numbers of electrons. They fill up like this. So the next element along, which is neon, oxygen, sorry, we'd add an electron here. Okay. You can't have more than 2 per orbital, so even if it's 3d that's got 10 orbital, holds up to 10 electrons, 5 of these boxes, each one would have 2, no more than 2. And I think that's it. So this is an electron configuration or arrangement, writing it all out, abbreviating it,